Hi, I've got a real interesting bit of kit for you today that I'm going to actually install in my house for my solar battery backup solution. But before I install it, I thought I'd show you what it is and then do a teardown or how it works in its operation, and then do a teardown of it to show you how it works inside because, well, I don't know because I haven't torn it down apart yet. This is what's called an automatic transfer switch. It's got two different mains inputs. It tells you here with nice infographics, connects to the city power grid and also a backup generator. That it's a DIN rail mount thing. It's about $50 Aussie or something. You might be able to get it cheaper than that. It's got a manual or an automatic mode, so you can manually switch between source A, the grid, or source B, the backup generator, but it can do this and sense automatically. Hence why it's got these sense wires coming over here to some internal, well, maybe electronics, maybe not. Maybe it's some dumbass like diode relay logic or something like that inside, which is probably more like what I'd expect. But anyway, we'll see. So we've got our grid and power input here, active and neutral here. They just call it AL1, active line 1, I guess. And then we've got our second input here, which is comes from our generator, but we can actually reverse this. And this is how I'm actually going to use it. I'm going to use it reverse, but I'll explain and show you that later. So the second input here, and then the output, which goes to your load, is down here, which you want to power and have backup of, which is what we're going to do. In my particular case, I'm going to be powering some fridges. So this is actually a 2-pole one. You can actually get a 3-pole and a 4-pole one as well if you want, the additional phases or whatnot. So it breaks the neutral and it breaks the active as well. So depending on which source you select, either this one or this one, it switches it through to here. And so both of these devices all in here are just going to be a big like mechanical selector switch, just switching either of these inputs to the output. Easy. Let's go to the DaveCAD and I'll show you what I'm doing here and an application for one of these automatic transfer switches. So this is for my particular application, okay? You can actually install this for different types of applications, but this is what I'm going to be doing at home. What I want to do is I've actually got 3 fridges and freezers at home, and I want to power all of these from my new 3.6 kilowatt hour backup battery that I've got, which you've seen in the previous teardown video. Link it in if you haven't seen it. So 3.6 kilowatt hours should just be enough, and I just tested it last night actually. It did actually last. Should be enough, and I'll do another video running through the numbers, the consumption figures, and figuring out what size backup battery we need and everything else. But anyway, that won't be this video. So what I want to do is disconnect the fridges from my house circuit entirely, okay? So this is your grid coming in here to your fuse box here, and normally the fridges would just be plugged in as, just yet another load inside the house. But I specifically want to power these like all day, every day from my battery, and I want to charge my battery from my solar system during the day and use that energy at night. And we don't actually need this automatic transfer switch we've shown here to actually do that, but I'll explain why it's vital, actually, to have one of these things. Otherwise, you're going to come a gutser. Now, this is totally different to what's called an AC battery solution for your house, like a Tesla battery or an N-phase battery, for example. So we're not going to look at that, and this is not the same as a hybrid inverter, which I'm looking at installing as well with an additional backup battery. This is just like a standalone independent thing I want to do with these fridges because I want to utilize more of my solar output, and I want to lower my grid consumption, because at the moment at nighttime, remember, all your fridges and freezers, they're running 24 hours a day. So during the day, my solar, I've got 2 different solar systems. One's the N-phase microinverters, the other is the Sunny Boy string inverter, but it makes no difference, okay? I've got 2 different inverters which then put the power onto my fuse box, essentially like in parallel with the grid and everything else. And everything I power during the day include, I didn't draw my little ionic EV here. I've got my Zappy charger, which actually tracks with the solar output with current transformers on there, and it allows me to modify the current going into my EV to actually match the solar output, the excess that I would otherwise be wasted, pissing away, feeding it back into the grid in that direction and getting paid an absolute pittance for it. I want to put it into my EV, and I want to put it into my battery to power my fridges at nighttime. So what I've done is I've totally disconnected my fridges from the rest of the circuits in my house, and they're connected to the output, the 240 volt inverter output of my battery generator. So just imagine that transfer switch is not there, okay, like that. And you could, as I said, you don't need the transfer switch. I can just connect the fridges directly on the outlet here. And also this provides some backup power points just in case the grid power fails. It's people ask, but it's incredibly rare here in Sydney. Like, I've lived here all my life, and the biggest power outage we've had is like 5-6 hours, maybe, and they're incredibly rare. Okay, so that's why I don't need like a whole backup solution for the whole house, and because the power fails all the time. It does happen, like up the Blue Mountains, for example, or other remote areas and stuff like that. Yeah, your power could be intermittent. In Sydney, it's pretty schmick. So anyway, I've got a backup power point, and I want to power my 3 fridges, say that 3 times quickly, 3 fridges 3 times quickly. I want to power those from my battery. Now, I have actually done the calculations, and I'll go through it in another video, but the 3.6 kilowatt hours is enough to power these fridges overnight. But before I get into the complexities of my solution, right, just imagine that automatic transfer switch is not there, and you're happily powering your fridges, right? You get enough power in during the day to recharge the battery, and then at night time the fridges are just powered from that, right? Because the battery that I've got, it actually during the day, if you keep the mains connected here, if you actually keep it plugged in to like the grid here, it will actually just supply, it'll keep the battery topped up to 100% or 90% or whatever you set it to, and then it'll supply the fridges. Anyway, I'll explain how I'm going to do that in a minute. The automatic transfer switch, okay? If you don't have this, right, if this didn't exist and this was just wired straight through to here, what happens if for some reason something happened to the generator and the power, I don't know, it fails. Somebody pressed the switch, or, you know, there's an internal circuit fail, something happens or whatever, or it didn't get enough energy during the day to charge it, or, you know, there's quite a few things that can go wrong here. Then, if you're not alerted to that fact, then your fridges are going to defrost pretty quickly, and you're going to lose all your frozen stuff. So yeah, that's going to ruin your day. So what the automatic transfer switch, by putting this in here, does, it has a priority input, which I'm going to set as my battery. So during normal operation, the priority input comes from the battery, and that powers the fridges during the day. As I said, it can be powered from the solar like this automatically. If this battery fails, or it goes flat, or does whatever, you know, something, you know, there's a lot of complexity in here. It's got a battery, it's got an inverter system, it's got a charger system, you know, there's a lot of stuff that can go wrong. So if for some reason this does fail, this automatic transfer switch, which we've got here, it'll automatically detect that the generator input has actually, which is the battery, has failed, and then it'll automatically, within like 50 milliseconds or so, it'll switch over to the grid. So it'll keep these fridges and freezers all running regardless of what happens. And then as soon as the battery comes back online, i.e. you might start, somebody tripped the cord or whatever, right? And you fix the problem, you plug it back in, well, it'll automatically detect, because this is the priority input, it'll automatically detect that, hey, my battery system's back up, I'm going to switch from the grid back to the battery. And that's what these automatic transfer switches do. They're very cool. But ordinarily, you would use them the other way around, just like what's shown actually on here. Normally, the city power would be the priority input. And then only if the grid fails, then your backup generator will kick in like this. But I'm actually going to use it reverse. I'm going to actually plug my battery into the priority input, which is the city power, and then have the grid as my backup power. And you can do that. It doesn't know the difference. In fact, if you have a look at the instructions over here, it kind of, in Chinglish, it tries to actually tell you this. Normally, you've got the city power, and then source B is the backup power. But note, for solar type, the backup power must be connected to the city power. So it's basically implying that the city power is the priority input. That's basically what it's saying. If you had another brand of one of these things, its instructions might say, you know, priority input, you know, backup input, something like that. Anyway, those who had their thinking caps on might see a problem with my setup that I want to run here. Okay, during the day, this sun hits the solar panels, inverter, it charges my battery up to, you know, 90% or whatever I've set, 100%. Okay, then, but at night time, it won't come from the solar anymore, it'll come from the grid. So this battery will never be used to power the fridges, huh? How does that work? Well, what I'm going to do is I'm going to stick a mechanical timer in there, mechanical or an electronic timer or whatever, and I'm going to set this to actually disconnect at like 4 p.m. in the afternoon once the sun's set, and then I can switch it back on at 9 a.m. or whatever. So from 9 a.m. to 4 p.m., for example, yes, it'll actually slow charge, maybe like, I think I have to run the calculations again with the third fridge, but like 400 watts should be enough during 9 a.m. to 4 p.m. to actually fully charge the battery and then have enough power for the nighttime. Just based on calculations and measurements of the consumption of the fridges, then I can actually tailor this time and this charge level to actually be enough, with some contingency added on, so that during the day, like even on the most cloudiest, overcast, crappy day, I'm still going to get like 300-400 watts out of this, and I can dump that all into the battery. So at nighttime, I can just use a simple mechanical timer, and bingo, I've got myself an independent battery backup solution that powers all my fridges from my solar and from my battery without having to have some smart-ass AC battery system and stuff like that. So you could do this, you could implement it yourself in pretty much any scenario. I think it's really cool. Anyway, I will do it when I install this thing. I'll show you an installation and testing and measurements video and all that sort of jazz. For those that want to see it, there's the entire sheet there, and what's on the other side, I don't know. At least it's all in English. Anyway, for those interested, it does actually come in different models. I've got the 63 amp jobby here, I think. It looks like it's breaking current here, 50,000 amps, kilo amps. Thank you very much. It's rated for 8 kilovolt impulses. That'd be for, the electronics and whatnot, or it doesn't arc over or whatever. Anyway, its transfer time is 50 milliseconds. So this is just basically like a relay operation. You can actually get much more expensive versions of this, which are electronic versions, which have zero switchover. They're designed for like real critical backups, like if you've got a big server rack or something, like you can't just have a big clunking mechanical switch going vroom, thump like this. Your server's going to hiccup or whatnot. This will be a break before make system, so yeah, you can't rely on that. And it looks like it also has a single pole double throw relay on either side here, so this would be for like external indicator lamps. Like it's got internal indicator LEDs here, but yeah, you can hook up big, like if you wired into a big panel or something like that, you could have a big flashing, rotating light that the power's failed or whatnot. Okay, so let's demo this before we tear it down, shall we? I've got my high voltage differential probe on the output here. I don't have any load. It makes absolutely no difference. Then I've got a black mains cord input here. That will be the generator, but in this particular case, this will be my the grid in my particular application, and then the grey one up here will match the grid up here. Okay, so let's put it in automatic mode here, and we'll just so we'll plug in the generator. It's currently set to the generator, so it shouldn't flip anywhere. Okay, there we go, and there's our mains up there. So of course, if I wanted to, I could switch over to manual and go clunk like that, and the output is disconnected, and I can clunk it back like that. It looks like this just indicates, it doesn't indicate which one's on, it just indicates which, like, that there's actually power active there. Now, if we switch this back to auto mode, then the priority input should be this city one. It should be this grey one. So at the moment, it's back to the generator, but it should switch back. So this is how, like, you'd normally use it, okay? The mains grid has failed, it's come a guts, someone's ran into the power pole, and the power's failed, right? There's a lightning strike somewhere, transformer's been taken out, you're on your backup generator, but then the grid automatically comes back on. Hopefully, it should detect this and switch. And it does. Whoa, that was pretty violent, wasn't it? And you probably saw that there was actually a changeover time there. But let's look at my configuration where my battery will be the city grid power. So this is my battery here, and let's say that my battery fails. Well, it's going to... boom! It physically, just see it jump, physically vibrates in there. There must be a huge spring mechanism in there. So anyway, that'll be an interesting teardown, but you can see that, yeah, that is just going to come back. Okay, so we're currently sourcing from the grid, okay, and if our backup generator fails, nothing happens. If we do that, then, and we're from source B, it will, boom, go back to the priority source. Okay, so let's see if we can actually capture the mains switchover time. So I've set my trigger here to actually pulse with negative like this, and I set it like 8.8 milliseconds or something like that, and that should, hopefully, capture. So single shot capture. Let's give it a go. And boom, there we go. Our switch over. And you can see this was before it was coming from source A, so it was coming from the grid. And then it's 20 milliseconds per division. So it took about 20 milliseconds or something like that to switch. You can see some switch bounce in there. No wuckers, that's what you'd expect, like some contact bounce. It's, as I said, this is not an electronic switch. This will just be like, as you can hear, a physical thumping mechanical switch. So yeah, it has actually switched from one source to the other, even though it looks like the same source, because it literally is, because we've plugged it into the same mains board here. But if you had different source voltages, different source frequencies or whatever, and they were asynchronous, then you would see it change. And there's the other direction. I think that's a bit quicker. They're 5 milliseconds per division, 5, 10, like 8 milliseconds or something, to switch from the backup grid back to the priority source. Well, there you have it. Isn't that interesting? We've got two big solenoids here. Like it had to have some sort of spring type system. And sure enough, if I rotate that, you can see that that shaft just rotates like that. And of course, the big thump and bounce that we saw is just like the solenoid acting so quick that it just pulls it in one direction or the other like that. And there's a shaft there with two little micro switches on it. So maybe that has to do with like the actual reverse in action. That's part of the logic, maybe. I'm not entirely sure. And like, as I suspected, there is like no active circuit. It doesn't look like there's any active circuitry in here. It's all like relay logic. Are they diodes? Yep. So it's like some sort of diode relay logic type thing. And this is interesting. Check this out. This is the load output here, and they've actually got huge big braided, it's just welded onto that plate there, and that can't see how that goes down to the bottom side. The reason that they do that is so that you've got some compliance when that moves, because this is rated for, I think, 5,000 cycles. So, when this moves back and forth, even though it doesn't move a lot, right, there is going to be stress in there. So that needs to, expand and contract, and of course carry the maximum rated current as well. So yeah, there's just a big contactor plate inside there. So the whole assembly actually just lifts out. And yet there's no additional stuff on the bottom. We'll reverse engineer this in a sec. Oh, okay, so this relay here, which I thought was NEC, but it's not, it's NNC. Thank you very much. Yeah, that's actually doing the normally open, normally closed contacts, the auxiliary contact. So is that also powering the solenoid? Anyway, we'll find out. Giant lever in there, which just goes ka-clunk, ka-clunk like that. So yeah, you've just got alternating fields on these, and then it just goes doop, doop, slam like that. So as one pushes in, the other pushes out. They're physically connected, and that's just connected to the manual switch on the bottom like that. And there you have it. We can actually see inside. Watch this come over. Look at this giant arm like that just come over, boom, like that. So that's what takes the tens of milliseconds to switch over, and they've got giant pads in there. Check out the size of those pads. So they're absolutely enormous. So yeah, that's very simple. There's nothing else in there. I'm not sure what these are. They're just strengthening bars, are they? They don't look like part of any of the current carrying capacity at all. So not sure what's doing there. All right, so I've reverse engineered this. It took quite some effort. It's fairly obvious once you know, but to actually get it right, I had to desolder the relay here, and so hopefully I've got an exact duplicate physically of what's happening here. These red wires, this red side is the grid side here, and these blue wires and this blue solenoid here is the backup side. And we've got DaveCAD here. This is the rare portrait version, none of that landscape rubbish. So yeah, quite rare to see it here. I believe I've got an exact duplicate here. So we've got the two solenoids up the top here, like this. We've got the lever arm here, and I've got it in the grid position over here, okay? So we're going to assume that we have both power connected to the grid and to the backup as well, and our switch is physically in the grid position, okay? So it's all operational, it's powered up, and we're going to assume that our switch is in the automatic mode as well. And I've shown this auto manual switch here is this switch here. So I've put it in the auto mode here. And interestingly, it turns out that the auto manual switch, all it does is simply disconnect the solenoids. It completely disconnects them. Once you put it in manual mode here, you'll see that it disconnects the solenoid through each solenoid is powered via a diode bridge here, which is effectively like straight across the main. So this is the backup mains input, live and neutral, grid mains input, live and neutral here. And the relay is down here, and that's this relay here. I haven't drawn in those extra auxiliary contacts because they have nothing to do with the actual operation of this. Suffice it to say, this is a 4-pole double throw relay in there. And there's 2 MOVs in there across the diode, the AC input to the diode bridge. They're the 2 blue MOVs there. There's 681s, which is about 480 volts RMS jobbies. And by the way, there is the lead here is simply a lead and a dropper resistor. That's it. It's a 150k dropper resistor and a lead across both line and neutral here. I'll just leave those out for simplicity. Because as you saw, those LEDs don't actually tell you which one's active. They just tell you that you've actually got power coming to the input. So they're just straight across there. And then we've got our 2 micro switches here. These are effectively like end of throw limit switches. So they actually come on. They're actually normally closed switches. So in this position here, in the grid position, this micro switch is actually active, but because it's normally closed version, when you activate it, it actually becomes open. And I've physically demonstrated this here. How it works is slightly different, but I think this is a better representation. With the armature in the grid position like this, it's going to actually close the micro switch for the backup solenoid over here. So I've, as I said, I've put all of these switches in the current grid position. So the backup micro switch is enabled. So the solenoid for the backup solenoid here is sitting here ready to be engaged. But neither of these, during static operation, when it's not switching, neither of these are energized. So this is actually quite clever. Stick with me. Now, the relay coil, these 2 pins here, they're actually connected across the grid side. This is why the grid side is the priority side. So you want your priority source to be connected to the relay. So we're assuming that we have got our grid power here, our priority power source is active, and that pulls, it's normally here when you de-energize the relay, it's normally in the backup position, but when you energize it, when you apply power to the grid, it pulls the contacts this way, and then it's in the grid position like this. So at the moment, the bridge, the diode bridge here that's powering the solenoid here is actually on. You can see it's physically connected through to here, okay? So it's energized, but the micro switch here is disconnected, so the solenoid's not active. And likewise, the backup solenoid here, while it's connected to the diode bridge is unfortunately not activated because it's disconnected here because it's in the grid position, so it's open. So what happens if the grid, the main priority power source, fails? You remove the power from here, well, the relay suddenly switches, de-energizes, and switches back over to here. So what that does is instantly activate the apply power to the diode bridge for the backup side here, and because this micro switch is physically closed by this lever here in this position, okay, as soon as this power fails, then this diode bridge is going to get power to it, and this micro switch is closed, and this solenoid is going to activate, and it's going to go ka-clunk and pull this armature from here over to here. But of course, it's going to take time for this arm to physically travel all the way over like that and deactivate this micro switch and activate this one, okay? So it's going to take, like 10 milliseconds or something like that. So the solenoid activates briefly, and then the armature starts moving, and when this micro switch disconnects, there's no more power for the solenoid, but the solenoid's done its job and effectively latched the switch over into the other position. Neat. So it's like a latch-in relay. So this micro switch is now closed like this, and this solenoid is sitting here waiting. Oh, come on, give me power, so I can switch from the backup back to the grid side. And of course, because this is the priority power source, it has the relay coil on it. So as soon as the line workers are finished fixing the grid, good on ya, champs, then it applies power back onto here, and the relay flips back, and then this solenoid activates very briefly, and it goes clunk back into the other position, and it's reset itself. So it goes flop like that and flip backwards. And it's basically a latch-in relay like that. That is a really neat system. I like it. It basically relies on the physical time that it takes for this thing to, travel over. You saw it on the scope there, tens of milliseconds or whatever, but that was enough time to activate the solenoid and pull that armature in and clunk. And when it's static like this, none of these solenoids are active. And of course, if you switch this to manual position, it just disconnects the diode bridges. They're not connected anymore, so you can just manually just go clunk, clunk like that, and it makes no difference to the relay circuitry at all. Wait, hang on, we've got a bonus. We've got a different brand. Let's see if it's the same. It looks very similar. In fact, the boxes are all near identical. This here is the box for the new one. It's an automatic transfer switch, dual power. This is the one we tore apart before. The dual power automatic transfer switch. So yeah, I'm going to guess that this one is more of the real McCoy genuine article, and this one we looked at before is the Dodgy Brothers cheaper one. So let's quickly open this, and as you can see, it's actually it looks a bit better. I prefer this switch to the other little slidey switch over there. This is much better, and this is physically really hard to move. Wow. And on the bottom here is a bit different. It uses a better quality DIN lock-in mechanism. It just looks and feels like a better quality unit than what we just tore down. So inside, it looks like the operation's going to be absolutely identical. I wouldn't even bother reverse engineering this, but I like how it's got separate boards off here. The diode bridges are off on a different board. So let me get that open. That's just a relay board. It looks like it doesn't have the auxiliary contacts. That's only a 2-pole, is it? Rather than a 4-pole we have before. But look, it's basically exactly the same operation. We've got the lever arm here, which is much more difficult to pull across like that, but it basically works absolutely identical. So it's got the override switch here, and this is why its lever force is not as good as the other one, so it requires more force to actually change it over. But they've got the bridge down there and the MOV on a separate board like that. But check out the limit switch here, like the end of travel switch here. It's like a big PCB, big blocky PCB mount thing. I've never seen one like that before. I'm not going to take it apart further, but yeah, you can see the armature in there. It works exactly the same way as the other one. So yeah, but I like the look at that. That micro switch just looks bigger and beefier. But if I'd have to guess, I'd say this is the real McCoy. Does it have a brand? Doesn't actually have, I have to get the documentation. Anyway, I reckon that's the real one because it's a transfer switch, not a transfer switch, like that. And that, yeah, so there's no fuel one. I think it's a slightly cheaper knockoff of this. This might be the original one. I don't know. If you know the history of, who is the originator of this actual design, then please let us know. But there are significantly different implementations there. I can't get that. I don't know how to get the rest of that switch open. I think I'd have to destroy the whole lot. I'm not really interested in that to look at the actual contactors in there. But yeah, I think this one, it's the vibe. The vibe of this one is better. But there you go. I hope you found that interesting. Automatic transfer switches, absolutely fascinating, and they're really simplistic, but incredibly clever how they actually work, these things. You've got your priority source, and it's just basically a latch-in relay type system, so to speak. So, fascinating. Hope you liked that. If you did, please give it a big thumbs up, and as always, discuss down below. And I don't do it very often, but thank you for all my patrons over at Patreon who did help keep funding this, whatever it is I do. Catch you next time.